Okay, so today we're going to start building up towards our analysis of electric circuits. And this is 802. This is not a course in circuits, but our goal in 802 is to get you to the point of understanding that all of the basic analysis of how batteries, resistors, capacitors, inductors, the basic circuit elements, how they work and how they behave in a circuit, it's all Maxwell's equations. That's what we're aiming to do in 802. And then the other half is to give you a sense that we've given you the basic fundamental tools for analyzing any circuit, although the circuits that we analyze here will only be rather simple. If you go on and take a further course in on circuits themselves, there will be much more complexity that you can add later. So our first step in this journey is batteries. What's a battery? Well, sort of this is a battery. This is my hand-drawn cartoon of a car battery. It has a positive terminal and a negative terminal. And a battery, one way of saying it is a battery is an exception to something that we've told you probably about 100 times up to this point. And it's an exception that we didn't mention until this moment. What if we said, if we have a place right here where the potential is positive, and we have a place over here where the potential is negative. So over here, the potential is larger than over here. Then up to now in 802, what have we taught you? We've taught you that if the potential is higher here than here, then positive charges will flow from the high potential down to the low potential. So based on what we've said to this point, if I just tell you potential is high here, potential is positive here, potential is negative here, that means positive charge should flow from the plus to the minus. And this box here, this battery, is a region of the universe in which the opposite happens. What is actually happening in this battery is that positive charges are being carried from this end to that end. So that means that there is some agent inside the battery which is transporting charge against the electric force, against the Coulomb force, against the potential gradient. So maybe there's a little person in here. You can think of a battery as inside this box there are these little people, and they're carrying the positive charges from the negative terminal to the positive terminal. So even though the potential is higher here than there, we've got little people inside, and they're carrying the charges from there to there. Of course, there aren't little people inside a car battery. There are chemical reactions. Ditto for a standard 9-volt battery or 1.5-volt C cell or AAA. Same for the lithium-ion batteries that power your cell phone. In all of those cases, the forces inside here that are transporting charges against the against the potential gradient are chemical in nature. There are other kinds of batteries not familiar from daily life where it's nuclear forces that are responsible. There are other kinds of batteries. They're not usually called batteries. They're called solar cells, where the forces that are inside a solar cell that are carrying charges up to the positive terminal, positive charge to the positive terminal, are being driven by the energy of light from the sun. Whatever the nature of what's going on inside, there's something which goes beyond electromagnetism happening in the box. You can think of it as little people if you like, although it's in no battery that I know is it actually little people. There's some non-electromagnetic agency, non-electromagnetic force, which is pushing positive charges up to this terminal, even though this terminal is at a higher potential. And that's what a battery is. So the way we use a battery is we connect these two terminals, plus and minus, with wires to some device that we're trying to run, that we're trying to power. This device might be a light bulb, might be a resistor, might have capacitors in it, might have inductors in it, it might be a cell phone, some device. And the whole story then is that inside the battery, I have some non-electromagnetic agency, those little people, which is taking charge from the negative terminal to the positive terminal, even though the positive terminal is at a higher potential. And then outside the battery, the these charges flow downhill, down the potential gradient from the positive to the negative as we have taught you. And along the way, they're going to do something useful for us in this device. So this is the essence of a battery. Now, when we draw circuits, we don't want to have to keep drawing boxes like this. So there is a standard conventional symbol for a battery in a circuit, which looks like this. And by convention, the longer plate here represents the positive terminal, and the shorter plate here represents the negative terminal. And this is the standard way of representing a battery in a circuit diagram. And what does it mean? It means that a battery is a device which maintains a potential difference between this spot in the circuit. We can call this V of the positive terminal. We can call this V of the negative terminal. And a battery is a device which maintains a potential difference between the positive terminal and the negative terminal. And this potential difference is conventionally called the electromotive force. We need to call it something. We're going to be naming it all the time, so it's good that it has a name. But it's actually a bad name because the electromotive force associated with a battery is not actually a force, it's a potential difference, as you can see from its definition. But we live with the terminology that we have inherited. So a battery is a device that maintains a potential difference between this point and this point, referred to as the electromotive force of the battery. And then we can connect this battery through a circuit to other elements, which we'll begin discussing in subsequent videos. And inside the battery, there are non-electric forces that are taking charge from here to here. Outside the battery, this is a higher potential, this is a lower potential. So if I connect the circuit through, let's say, just a single resistor, then outside the battery, positive charge is going to flow from the high potential to the low potential, and in this case, it's going to flow through this resistor.
Let's look at a circuit in which we have a seed of EMF that we're going to look a battery, and here we have a point, let's call this A and this B, and we know that the terminal potential difference for an ideal battery is equal to the electromotive force. Now remember, electromotive force is not a force, it's the energy per charge in moving a charge across the terminals from, this is what we call the negative, to the positive. So this is our ideal battery. There's no resistance in this battery. And now we want to connect this battery to, we could think of it, these are our terminals. And we connect this terminal to a wire, and in that wire, there's a circuit element, which we're going to refer to as a resistor R1. And here, let's call this point C. Actually, we'll call this point D, and this point here C, and that point D. And I'm just going to connect it to another circuit element. And again, this another circuit element, it may be a light bulb, it may be a rolled resistor of some type. This will be a second resistor, R2, and we'll come back to where we are. Here's D. I'm going to call this E. On the other side here, F, and then I'm back to A. Now, when we analyze circuits, we want to talk about the potential difference as we go around this closed path. Now, we know in electrostatics that the line integral of d dot ds is 0 around the closed path. And recall that when we talk about potential difference between any 2 points, V, say D minus V of C, that's the integral from C to D of the electric field in going from one point to another with a minus sign. So the fact that all of the potential differences around a closed sum up to 0 is just a statement that the line integral of E around a closed path is 0. So that fundamental law of electrostatics is translated into the statement that the sum of the potential differences around a closed path, I, however many we have, is 0. And now we can also, we want to apply that to this loop. But what's important to realize is that here, our wire is, we're assuming that this connection between B and C, this is a resistanceless wire, R is essentially 0. And so that tells us that the potential difference at C is the same as the potential difference at B. The potential difference at E is the same as D. The potential at F is the same as A. And what we see is that the potential is increasing as we cross the CDVMF, and the potential is decreasing as we cross a resistor. And it decreases as we cross the resistor, because in this case, the current I will flow, and I flows from high potential to low potential. And so as we cross that resistor, the potential should drop. So let's just make a graph and see what happens with the potential. This is not in time, but it's in space. And we'll start at our point A. Now, we'll call the potential here at A, V equals 0. So we're arbitrarily going to call that our 0 point. And so when we go from A to B, we're crossing the C to VMF, and our potential is rising to a point E. So we get a potential increase at B. Now as we go from B to C, that's along our resistanceless wire, and the potential is staying constant at C. Now when we go from C to D, we're crossing a circuit element, the resistor, and there's a drop in potential here, and let's just make a note of that. The potential on the lower side of the resistor minus the potential on the higher resistor is I R1. That's Ohm's law. Now we go from D to E. So here's E. Potential is constant along our wire. Again, we have another potential drop. Notice that when we go from E to F and F back to A, I'm just jumping ahead a little. These are at the same potential, and that's back to our 0 point. And so when we're going from E to F, if the sum of the potentials around the closed path is 0, we're dropping down to 0. And this is a graphical representation of the idea that the potential drops around the circuit, this single loop circuit, are 0, and it amounts to the following statement, that plus E minus I R1 minus I R2 is equal to 0. And that's an example of the idea that the line integral of the electric field around a closed circuit path is 0, where there's a steady current flowing. When we were looking at Kirchhoff's law, that the sum of the voltages around a closed path is 0, one of the issues that come up is when we cross a battery, is the voltage rising? Or do we use a positive EMF or a negative EMF when we cross a resistor? People say voltage drops. Do we use a positive IR or a negative IR? In order to settle these issues, what we want to do is introduce some conventions. Now, these conventions are very similar to the conventions that we use in mechanics or in anything. It's like our coordinate system for circuits. So here's how we do it. So let's take a very simple circuit first. With a battery, a CDVMF, and just a resistor for simplicity. Now, there are two choices that we need to make. We need to choose a direction for current. Now, I do that by indicating on my diagram here, because this is the positive terminal, it's pretty obvious that the current will leave from the positive terminal, go back to the negative terminal. So you might say, why are we making this choice at all? But let me remind you that if I had two batteries and a resistor, and these batteries had different EMFs, would you know which way the current is flowing without knowing beforehand which EMF was bigger? So again, I could just arbitrarily say my current is going to go this way. And what that would mean is that this battery is discharging, but this battery is charging. So this convention gives us a reference frame for current. And the important thing to think about is the following, that if we end up solving for I positive, then the current flows as shown. And if I is negative, the current actually flows the other way. So in this example, I would expect to solve for an I positive, but in this example, if I solve for I positive, the current really goes that way. If I end up solving this problem and I get I negative, the current goes in the opposite way. So this is our first convention for defining I. Our second choice is a little bit more complicated, and I'll just write it down first and then explain what I mean. But we choose a circulation direction. Now, that's not the direction of current. And the reason we do this is, first off, conceptually, remember that the sum of the voltages around a closed path is a line integral equal to 0. And in any line integral, you can go one way or the other, and that's a choice one makes. Now, what we want to do is we want to talk about voltage differences across elements. And in order to define what we mean by the voltage difference, let's take an element here, and let's say here's a point A and here's a point B. How do we define, do we mean VB minus VA or VA minus VB? That's the ambiguity. Now, choosing a circulation direction will enable us to have a definitive direction. So in this picture here, I'm going to choose a circulation direction. I'll write it as CD. Clockwise down here, for instance, that's a circulation direction. Now, when I choose a circulation direction, so let's look at our element will now be a battery, plus, minus. We'll call this point A, this point B, but so far we don't know what we mean by voltage. Suppose I'm circulating this way. I'm circulating from the minus to the plus. The circulation direction across the element defines an after side and a before side. And what we mean by delta V, so here's what we mean when we talk about a voltage element across an element, what we mean is V after minus V before. And this will enable us to unambiguously describe what we mean for voltages, differences across any circuit elements, batteries, resistors, and now we'll spell out that list in more detail. We now want to define how our convention for crossing circuit elements based on our two choices, current and circulation direction. So let's begin with the battery. So we have plus and minus. Now, I want to circulate across this battery in this direction. That's my circulation direction. This is the after, and this is the before. And the battery has some EMF E. So what we now see that our change in potential across the battery, this is our first example. We'll call this 1A. When you're circulating from the negative to the positive terminal, then the V after, I'm going to spell everything out for the first time, but afterwards make this more concise, before. The potential on the after side is the positive terminal. The one on the before side is the negative, So that's equal to the plus EMF. And so we say that we're raising the potential as we cross the battery in the circulation direction from negative to positive terminal. Now, our second example is what would happen if we circulate from the positive terminal, this way, our circulation direction, from the positive terminal to the negative terminal. This is now the after side. This is the before side. And you can see when we circulate in this direction, V after minus V before is less than 0. And so our second case, 1b, is that the potential difference across the battery is equal to minus E when we circulate from the positive terminal to the negative terminal. Now, what's important to realize is that the change of potential of the battery does not depend on which way the current is flowing, whether the battery is charging or discharging. It only has to do with how we're circulating around our closed path. Now let's look at the resistor, which will involve both of our conventions. So now let's look at a resistor. We'll call it 2A. So for a resistor, which we denote by our resistor symbol like this, what do we know about the resistor? First off, if we've arbitrarily choosing our convention, I to flow this way, then we know, you can imagine that this is the flow of positive charge. Positive charge goes from higher potential to lower potential. So this side is higher, and this side is lower. That's what our choice of I tells us. Now, if at the end of the problem, this is all a coordinate system for circuits, it's a consistency condition. Our second convention, let's say we circulate in the direction of current. This is defining the after. This is the before side. And so what we see here is that the potential difference here across the resistor, when you circulate in the direction of the current by Ohm's law, is minus IR. And sometimes people refer to that as the voltage drop. So again, it requires both conventions. We're circulating in the direction of the current, and the potential difference drops by minus IR. What would happen if we have the same resistor? We have a current I, that's the higher, that's the lower side, and now we circulate opposite the direction of the current. Well, this is now the after side, and this is the before side. And so now we see that the potential difference, delta VR, is plus IR as you go from lower to higher potential. And so these two rules are enough to apply Kirchhoff's law, delta VI equals 0 for any closed circuit path that just involves batteries and resistors, and that's what we'll work out next in an example. Let's now analyze the following circuit as an example. Let's suppose that we have a battery with an EMF, I1, a resistance, R1, another battery with an EMF of E2. Notice these batteries are pointed in opposite ways. And finally, a resistance, R2. So first off, we have two conventions to choose. And I'm going to choose my current to flow this way, and my circulation direction like that. And now I'm going to apply the principle that the sum of the voltages across each element is 0, where what we mean by delta V is V after minus V before, as defined by the circulation direction. So we can really pick any point to start. So let's start with the bat right here. As we circulate across this battery, we're going from the negative to the positive terminal, and according to our convention, that's plus E2. Then we're circulating across this resistor in the direction of the current, so that's minus IR. R1. Now we're circulating across this battery from the positive to the negative terminal, so that's minus E1. And now we're circulating across this resistor in the direction of the current, minus IR2 is 0. And so what we can do is solve for the current in this circuit. A little quick algebra shows that the current is given by this value. And now suppose that E2 were bigger than E1, then I is positive and the current really flows in this direction. That tells us that this battery is discharging and this battery is charging. Now, sometimes when we're looking at this circuit, you might think that there's multiple branches in here between the positive terminal and the negative terminal. But remember, inside the battery, there's ions that are flowing, and whether it's positive ions or negative ions, there's still going to be currents in this battery. So you have to imagine that this is just one path in this circuit. It's not multiple branches, but one branch in that circuit. And that's why there's only one current. A mistake would be to say somehow that I2 is flowing down here, but I'm going to put an X here because that's not correct. So this is the way we analyze circuits. You can see also the power of our convention. If epsilon 1 is bigger, the EMF E1 is bigger than E2, this is a stronger battery than that battery, then I is negative, and what I negative means is simply the current goes opposite our choice of direction for current. And that's a simple example for how to analyze a single loop circuit.